Hello students. Today I am going to explain about the phenomenon of refraction in ray optics. We know that when a beam of light falls on any transparent medium, a part of light gets reflected back into the same medium, while the rest enters that transparent medium. In the process of oblique incidence of light, that is, when light ray makes some angle with normal to the interface at the point of incidence, the direction of propagation of light ray changes. This phenomenon is known as refraction. For refraction also, Snell has given two laws. First law says the incident ray, the refracted ray, and the normal to the interface at the point of incidence all lie in the same plane. The second law says that the ratio of sine of angle of incidence I to the sine of angle of refraction R is a constant. That is, sine I by sine R is equal to mu, and this mu is a constant, which is the refractive index of the second medium with respect to that of the first medium. This relative refractive index is the characteristic of the given pair of mediums, and it is independent of the angle of incidence, but it depends on the wavelength of light. When mu is greater than 1, the refracted ray bends towards the normal. That is, when light moves from optically rarer to denser medium, as in the case of light moving from air to glass. Whereas, if mu is less than 1, the refracted ray bends away from the normal, that is when it moves from optically denser to rarer medium. Now, there is a practical activity of refraction through a rectangular glass slab. When we allow light ray to pass through the glass slab, we see that refraction takes place at two interfaces. First, from air to glass, and then from glass to air. We find that the emergent ray is parallel to the direction of incident ray, which means there is no deviation, but there is only a lateral displacement or shift. And this shift is with respect to the direction of the incident ray. The reason of no deviation is that in second refraction, the ray bends as much away from the normal as it had suffered bending towards the normal in first refraction. By using geometry, we can find the value of the lateral shift also, which you might have done in earlier classes. We have observed the phenomenon of refraction also in water-filled tank, where bottom of tank appears raised a little. In fact, the apparent depth h dash is equal to the real depth h divided by the refractive index of the medium. This relation also can be derived using geometry. The effect can be experienced on the steps of the banks of rivers or ponds. There are many more examples of refraction in nature about which you may think. Now students, your course includes refraction at spherical surfaces also, which I will take up in the next class. Right now, I would like to discuss one more very interesting phenomenon of light called total internal reflection. When light travels from optically denser medium to a rarer medium, at the interface, some part is reflected back into the same medium and the other part is refracted to the second medium. This reflection is called internal reflection. Since The refracted ray bends away from the normal while moving from denser to rarer medium. The angle of refraction is greater than the angle of incidence. With increase in angle of incidence, the angle of refraction is increased furthermore, and for a particular angle of incidence, the angle of refraction becomes pi by 2, that is 90 degree, which means the refracted ray goes along the interface of the two mediums, that is grazing the interface. This angle of incidence is known as critical angle. If now the ray arrives at the interface with angle of incidence greater than this critical angle, then the refraction is not possible, and then the ray is totally reflected back in the same medium. This is known as total internal reflection. According to Snell's law, as sin I by sin r is equal to mu, therefore for critical angle IC, the r is 90 degree. Hence, sin I is equal to mu, since sin r is equal to 1. So, we see that for I larger than IC, Snell's law of refraction is not valid, and hence refraction is not possible. Let us now think about the application of total internal reflection. Mirage is a good example of this phenomenon in nature. Usually in desert area and on hot summer days, when air is still, the air near the ground has more temperature compared to the temperature of air at higher levels. Hence, air near ground is less dense and becomes optically denser with height. As a result, light from a tall object like tree successively bends away from the normal and undergoes total internal reflection as the angle of incidence becomes greater than the critical angle. Consequently, to an observer, the light appears coming from a point below the ground and gives an effect of inverted image of the object in pool of water. This optical illusion is called mirage. Another good example of total internal reflection is the diamond. The critical angle for a diamond air interface is 24.4 degree, which is very small. Once the light enters a diamond, it undergoes total internal reflection multiple times due to spatial cuts of diamond, and hence the diamond sparkles brilliantly. But the most useful consequence of total internal reflection is the optical fiber, which is in great use of transmission of audio and video signals through long distances. The optical fibers consist of long fibers of glass or quartz in large numbers. These fibers have diameter of the order of 10 to the power minus 4 centimeter and refractive index of the order of 1.5. These fibers are coated with the thin layer of material of lower refractive index of the order of 1.48. Optical fibers are in the form of flexible cable, and the bundle of optical fiber is called light pipe. The light ray incident on one end of the optical fiber at small angle undergoes a series of total internal reflection as the angle of incidence each time is greater than the critical angle. Hence, the light travels to the other end of the optical fiber cable without any substantial loss of intensity. Even if the fiber cable is bent or twisted in any manner, the transmission of light takes place as the total internal reflection occurs without any interruption. Now, the application of these optical fibers. These are useful in many ways. In medical and engineering applications, it is very much useful. As it is flexible, it can be used to examine the inaccessible parts of an equipment or human body, like used in endoscopy. Besides being used for transmission of electrical signals converted to light signals, these are used to transmit images of the objects also. Optical fibers are used as telephone transmitting cables, and each fiber can carry about 2000 telephonic messages without much loss of intensity. Okay, students, that's all for now. Next time, I will take up refraction at spherical surfaces.